So, right, so where are we? So what, hopefully, I explained you gave you the idea of the programming language, and it was probably very quick, and I don't expect you to be able to program now. But so the takeaway points would be that what are the difficulties there? And I mean the idea that you have the execution model which has to be specified, and that you have lots of optimization you have to do. So far we haven't seen what they are. But basically we came up with a language that was supposed to, that is hopefully able to, and I'm still to persuade you into that. I'll give you the case study in Wi-Fi design to teach you a bit of Wi-Fi in case you don't know it, and also give you an idea how you can implement things like that in the language. But also, I mean, the high level is that you should partially believe me that you can implement lots of things, that the language is flexible, and it's easy to write, and it's easy to understand. But you definitely shouldn't believe me yet that it's going to be anything like efficient, right? So we just discussed that what you can use to write it, and hopefully understood the abstraction levels, right? And how to design control flow and everything else. But now, what I want to tell you is about how we actually compile this, and how do we execute it, and to persuade you that it's actually going to be fast as well. Okay, so how to write a compiler? How many of you have written a compiler? Okay, one, yeah. So I haven't done it myself either before this, so it was an interesting exercise. The first advice, always good to have a programming language person with you when you do it. So I mean, these guys, they did the first version in less than 2 months. An intern did it, right, in Haskell. And I'm sure you can use other libraries, but I was impressed. I thought, like, you have an intern for 3 months. There's no way he's going to write anything close to. The guy wrote in 2 months. He was producing code that ran in compiled in C. I was just impressive. So Haskell is a good language for that. I had to learn it, and it was because I was working with guys that are actually writing it only in Haskell, and I'm now persuaded that it makes sense if you write compilers to write in Haskell. And it has lots of support. Basically, it's written by programming languages guys that wrote it partially, that they're able to write fast compilers. And so you have libraries for parsing, you have libraries for code generation. You really write almost like C code in there, and it just gets replaced. And it has these flexible types and pattern matching that allows you to do very efficient, and I'll show you a little bit of it, very efficient and smooth kind of operations in there. And it's actually nice because the way they design the compiler now, and this is probably a topic for a PL programming language seminar, is that anyone can go and write an optimization pass now. Right? And it's fairly easy, right? So if you think of a new optimization you want to do, you have this abstract syntax tree, and you kind of add the optimization there. So that's the nice thing about easily extendable. And then again, what I learned from here is that this is compilers can be useful tools, right? So it actually does help. And so still the thing that I'm to explain you now is one can write, why didn't you write this in Python or whatever? So they choose a language of your own, right? So it's you can do much more things in the compiler, right? And it's not very difficult to do that. Okay? You need somebody who is experienced, but this idea started. So we started thinking about this a year ago. Right? We started understanding the problem, and we had a first version somewhere in September. Okay, and then now we have a release right in GitHub. So I mean, it's kind of something we are not too ashamed to give people to play with. So it's not a very long process, right? And there's we had 3 people for the first couple of months, and recently it's just the 2 of us. So it's not, and we did other stuff as well. So it's not too difficult. And now, some investment worth considering if you are ever going to coming into that area. And it was fun, I have to admit. I learned lots of new things. So never did that either. Okay, so so how do we do this compilation, right? So presumably, and I'll give you a little bit about it. So there's parsing, and all this is standard for the compilers. So how do we actually compile our language? What are the challenges there, and what are the optimizations we can do? So the expression language is the thing we use to define the code itself. If we describe FFT or this kind of block thing, and that's, as I said, pretty much straightforward C mapping, right? You do arrays. Okay, you need to do some mem copies and so on, but there's nothing much to think about there. There's some optimizations you can do on the code, and I'll show some of them. But once you have this code, and when we do optimization, we do all in our language. At the end of it, we have this imperative language. We just kind of pretty much straightforwardly map to C code. Now the interesting bit is this computational language. This is again that as I mentioned, this is the way we execute this tree that we have, this composition of these blocks in a correct and efficient way. This is the challenging part. And as I discussed with some of you, this is really targeted to a single core or maybe a few cores, right? But very powerful cores. We don't know yet how to do that on very multi-core systems, FPGAs and so on, but we are interested in going there and understanding that as well. So at the moment I'm going to describe execution model for pretty much a single core CPU. So this is what Sora and USRPs and of the world do at the moment, right? And then we can do numerous optimizations on the way, like vectorization, which is expanding the buses, sizes, and so on, lookup tables, and lots of conventional optimization that many other compilers do. These are kind of specific to our problem and to our domain, and I'm going to explain them all. So, right. So this is our Wi-Fi code. Wi-Fi receiver code. Hopefully now you understand a little bit better what these blocks mean, right? So here this will just going to be a horizontal thing. This guy is just a computer when it finishes. This guy is also a computer. When it finishes, passes on the control in here. So essentially it goes this way, right? So this is a transformer and a computer because they end where the header is ended. So both of them together is computer. This guy here is again a transformer. It inverts the channel, does all the OFDM channel equalization things. And then the code packet is at the end also receiving the packet. So as we discussed before, there was a question, is Wi-Fi a transformer or a computer? Essentially Wi-Fi conceptually is a computer because it receives a packet and it gives you a packet. So, but then if you want to receive more packets, you can put a repeat around this and then you dump more packets, so it becomes a transformer. So kind of but the question is how do we now run this? So we have to run, we get an input here, so maybe we run this function here, then we run one here, then we go and run one here, then we pass this here, or one has to go here, but then if it's done, if we detected a carrier, the next one should go here. So we're not supposed to take too many here in case we need to, if we overfetched and we need to go to the next one. Similarly, like if we have the case here, this guy decides when everything stops. So we shouldn't fetch too many things in this guy before that guy stops, and so on. So this is the main challenge of the execution model. So execution model is conceptual at this point, and I'll tell you basically how we do it afterwards. So you can think of these blocks as being some kind of small logic entities which have certain operations you can operate on them. And again, this is specially designed for a single core CPU or a few cores. I'm not talking about large multi-cores or so on. So what can you do? You can do tick and process. So basically it's like a box that reacts, and you can call a method tick or a method process. And at the end of this, it can return yield, skip, or done. So basically skip means, so yield, data value means I have a data value to give to my downstream neighbor. So if I have a link like this, if this guy returns yield, says, oh, I have something for B2. Okay. If I have skip, that means you either call tick or proc, or process, but I didn't have anything to do, so I just say skip, I don't do anything. I return a value which says skip. Or the last thing I can do, if you give me something and I say I'm done, okay? Don't call me again ever, I'm finished, I'm sending done, and with done I can return some control value, okay? So basically, and then process is called when you want to give me a data from the upstream. So for example, or you want to give me data from a side. So for example, this guy yielded some data there. So what happens then, this guy is called with process of this data, and it's processing this data. Right. So it's kind of not yet clear why we need all that, but this is the this is the definition of this execution model. Again, very high level conceptual. So a quick question, again, I don't know if you're able to answer anyway, but why do we need tick? So tick, basically, I don't give you any data, I just probe you, I poke you, kind of. It's to synchronize between blocks? Well, this is single CPU. Think of it that way for now. It's not synchronization because I run only one at a time. So essentially, I might have a code like this. Emit 1, emit 2, emit 3. So I'm just emitting, I'm not receiving anything. So I need to be flexible. I need to be able to express any code I want, right? So because of the potentially arbitrary execution code I can give, I need to make sure that maybe before that I was waiting for some element, but now I can have lots of elements to do, right? So I need to make sure that the order of execution of this is correct. So kind of formally proven that I will execute any code correctly. And so I think we have even a kind of a formal proof of this, but basically it's like you need to do a sequence of things. Whenever you call process, you need to call tick afterwards to make sure that because this guy moved after process, he did something inside. Does he have anything to send now spontaneously without even doing anything, or he has to give me another data? So basically what happens, first you call tick, and then if the tick is returned nothing, then you go process. If tick returns something else, then you can call tick again, because maybe we have 3 ticks here, and so on. So I'm not going to go into details of this. Just to give you this is just to give you an idea how this is done in general. You don't need to understand all the details, right? But the key thing is that we have some kind of state machine where all these blocks are in different states, and this state machine is supposed to describe this execution of this, and should worry about. So if you remember, one of the key things in the first part was when I give you the language, I don't care how it's going to be executed, right? Just has to respect the semantics of the language. And the semantics is kind of clear. Hopefully it's clear to you as well, but it's well defined what is going to happen, and it has to happen that way. Now we have to make sure it's efficient as well. And so the goal of this guy here now, okay, it's at this moment maybe it's not clear yet why it's defined this way, but if we call these ticks and processes in the right order, we will execute code in the right order. So that's the starting point. But then what we do lots of optimizations of this to kind of make a code very, very efficient. As efficient as we can. And the key idea is that this tick and proc, really, process model is really for the very non-optimizable thing. But there are lots of things in the code we will optimize. You can see that there could be potentially an efficiency problem, right? You need to tick and then process and so on. Whereas this is not our fast physical layer code, right? I was talking about these very fast things, and now you introduce all this complexity of this intermediate layer and doing some calling some things. But the key thing, we need to be efficient and correct, obviously. So this was to give us the correctness part, because now we know how to execute at least this correctly, no matter what code you give me. And then now I'm going to talk about optimizations. Right? So, yeah.
There is no input shown.
Sorry, but the input is in process. So if I call tick, I don't give you input. If I call process, I give you input. And now depends on which block you are. This process will be an input from a side or from the top. So, but not every time I call you, you'll have an input. Sometimes you might not, because of this, right? You can emit, right? So, and it would be functionally incorrect if I give you an input between these two. Because if I give you an input between these two, but you're first supposed to emit, and maybe some block downstream would react on this and stop the whole pipeline, and this guy who came in would have been incorrectly fetched. So I'm not supposed to give you an input before you do all your emits, because something can change in the configuration. So we need to respect this semantics of the of the program. And it's not immediately clear. This is again, this is just to illustrate conceptually how this is done. I don't think if you're interested in language later, you can understand the details of this. But this was just to illustrate the technique rather than really give you all the details, right? So just to give you an idea how this executes, basically, if you look at the code like this, so first of all, we start from all the way down. So why do we start from all the way down? Because this guy can emit something. Again, we shouldn't fetch data before we check that you have something spontaneously going on. For example, this guy should start sending a preamble. So we'll first start sending a preamble before we start encoding bits, because some code in the preamble might affect the rest of it. So we do a tick of this one. So this one says, oh, skip, I don't have anything to do. So then we do a tick of this one, because he's the upstream. He says, skip, I don't have anything to do. And test is, by the way, is defined here. Right? So then I say, tick this one. So this is our special control, which is an input, which always has something to give us. This is the general input of of the whole system, coming from radio or file or wherever you want. So then this guy says yield. Okay, I have some new item to give you. This is n. So then what we do, we say process with n, call this one process. So now this goes, this is a transformer defined here. Okay, so we put this message inside. So okay, we first process repeat. I'll skip that. It's just basically very high level. So now we process take. So take knows what to do with process. It will take the process element and it will finish. It's a computer that just takes one element. And if you remember, at this level, so we have this a little bit weird distinction between vertical and horizontal. Vertical is data path, horizontal is control path. So here we are in control path because that allows us to do different control changes to them. Once if you can think of it, if the data element is in vertical path, there are no changes, it just goes through. Once it goes in a horizontal part, there's a control element in it. So here it just takes it, but obviously there's nothing to be done here. So we could have done some processing here, some imperative code or something like scrambler. But done is just going to pass this value x to the rest of the code in this block. So then this is going to call process with this n on the next part. And n, why is this n? Because this is the parameter of this emit. So that's the value it takes. And then this is going to yield down the data path to the next thing as we required. And so on. Now it's going to call the process here and then it's going to emit. So again, I don't expect you to understand why this is a correct way of execution, but just to give an idea what is going on here, right? What is the kind of order of these events, how it's going to be executed. And this is the main loop which is basically running these things. It's going ticking and saying, you know, oh, you go here, you go there, you go here, you go there. This is again conceptual. This is not how it's implemented. In the real implementation, it's going to be a C code that does all that. It's going to, for a specific code, we're going to create a state machine that is going to jump around. But this describes the behavior of this thing. So there is something that is going to, what I illustrated in the previous example, I was saying, oh, now I'm ticking this, now I'm ticking that. This is this kind of main loop that is doing it. Okay. So this is enough about the execution model. So again, the message was just to understand how it is done to be correct. And now I'm going to tell you how we can actually make it efficient. So you say, there's so many ticks and procs. Why are you talking about real-time phi, right? I mean, you're never going to do that. So the first thing we can do is now we can go do lots of optimization around here. So, and this is what happens, right? So basically, what happens is that we take this abstract representation of this code and we go through it in multiple passes. And I'll give you an example how we do that. And we do transformations at this abstract level that are certainly not to violate the semantics of the execution model. So what does it mean? So for example, if I look at this guy here, now this is a repeat. And I can count the inputs and outputs. That's called static analysis. So I look at my tree and I can count and say, oh, this guy takes one element and emits one element. So if I have a repeat that takes one element and emits one element, then this is just a map, right? So if I take this x plus 1, so the whole thing here could be replaced with this thing here. So just one map. And by the way, this is the output of a compiler. I didn't write this, I just copied. So this is the kind of intermediate step. So why is map better than repeat, take, emit? You just saw. Repeat, take, emit has to tick this, proc this, right? But we replace this with just one auto map. There's nothing to tick and proc. Just give it, there's one tick for that. There's nothing else, right? And this is the source level transformation. So, but the key thing is now we know this is correct. And we have a representation that is correct. And we are starting from the correct representation, which seems complex. And it is if you don't do anything. But then you start trimming down and removing bits and replacing with more compact bits. And if you really have some very weird code, right, then it will remain complex. And that's why we are doing a domain-specific language for wireless. If you start implementing big data analytics in this, it's not going to do it, right? Because you'll have so much control flow that you'll have to keep these ticks and procs, and it's never going to be of any use. But the nature of our code that we want to write is such that in many cases, and we've done Wi-Fi and bits of LTE and so on, sorry, it can be actually very nicely optimized. And so and this is the thing, like if you think of FFT, right? FFT is going to do these takes of a large array, vector. It's going to process the vector and emit the vector. And that's going to be nicely converted into auto map on its own, right? And so, but you don't have to worry about it, right? We have this execution model that is correct. We optimize parts of it. Okay, so now we have these two auto maps. So we lost lots of these ticks and procs. and then we basically have two auto maps. Now, if you look at it from high level, what happens is there is a tick. We know that this guy doesn't have to be ticked because it's a map. It can only be proc. And this guy cannot be ticked because it's a map. It cannot emit spontaneously. It has a very well-defined thing. So the C code we write is really this. And there are two go-tos in addition. I just removed for, but this is again from the compiled code. You basically get input from read. You call this auto map. So this same variable is passed here. You call it and copy here. Then you call this thing as in the auto map, the other one. And then this function x plus 1. And then this one is being called input. So again, there's just two go-tos in between these two, which I don't show. But because we know lots of things about automap, that it cannot be ticked, it doesn't have to be, so we can simplify further this model and actually make it really execute only that. Now, the smart C compiler, and all of them are smart nowadays, will actually inline this, it'll become x plus 1, and inline this, it will remove all the indirections, and it will really become just get x plus 1 put. So it will be super efficient. But there are several levers. So we do one thing of the execution model. The C compiler will do amazing things with, on this inlining. I mean, if you run a C compiler with debug or release, be it GCC or Visual Studio, you have like at least an order of magnitude differences. I mean, unbelievable. So you need to make sure you compile in a release mode. So do all these sorts of optimization internally, and you just get amazing code, right? So of course, this is a simple case, right? So here's another thing we can do. So if I see that there is a times 4, right, and I take a certain element and I repeat it, right, so I can convert these times into a 4 in the imperative code. And I think I'm not going to go into details of this code, but the high level, okay, it's just that this is a computational language where I have to tick this, and I have to tick this inside. And if I see that it's simple code that could be transformed in an imperative code, and an imperative code is a single block of do, which compiles straight into C code, I'll replace this time with a for loop in this imperative code, removing all the internal control structures, and I won't have to do any ticks and procs. So there are lots of type preserving transformations we can do, if you start thinking about it, that we can do once we have this abstract representation, and we just prune and eliminate all these overheads. And again, our original execution model stays only for the most complex pieces of code that cannot be optimized efficiently otherwise. And hopefully, and in most cases it turns out to be like that because we are doing domain-specific language. This is only in the very extreme situations where, for example, at a very high level, where we do coding and decoding, or the packet header processing and so on, where we pay some penalty, but this penalty aggregated over everything else is so small that it doesn't matter. So, you can always do a little bit more better, you do a bit better, but, you would sacrifice this at the expense of clarity of the code and all the other nice stuff. And I'll show you the results, the performance results at the end, and we don't think it's worth it. So, okay, so we get, in this case, we get 3 times speed up because we don't do all these ticks and procs inside this one. So, how do we do this transformation or abstract syntax tree? So, I guess since no one has written, or one of you has written a compiler or something, it was kind of new to me, and I guess I had the undergrad course a long time ago. But basically the idea is when you get your code, you parse this code, and you represent it in something like this, right? So it's an abstract syntax tree, meaning that every single thing in a program has is an expression can be parsed and break down into something like this. So if you look at this one, for example, what this says is y becomes x of 0, 10. So this is notation saying take a subarray of length 10 from 0 to 9, okay? From x and copy into y. So I'm not even giving y equals. I'm only giving the subarray read, okay? So this is going to be in sequence with this guy here. Or it's not sequence, it should be, it should be equal. Anyway, I forgot that bit. So the array read has 3 parameters. There is an array from which we read. This is the branch here. There is a starting value 0, and there's the ending value 10. But then the array is not simply an array. We need to give a type of array, and here it's a type array. And if you put type in here, it's wrong. It shouldn't be here. The type checking should fix that. And there is type array, and there's a subtype, which I hid here. And there's this x. This is the name of a variable. And so the second parameter is a value. it's not a variable, it's a value. It could be a variable as well. We could maybe put here j instead of 0. It would be evar in this case. But now it's a value. And then this value is type int and it's 0. Right? And then the second parameter is value type, sorry, it's value int. It's also type int and it's 10. Right? So this is a kind of representation. And so when we parse our program, we do type checking. So type checking will make sure that all these types are reasonable, otherwise it will complain. So we have this big tree. And that the nice thing of Haskell is this, you can do very easy searching and pruning in this big tree. I'll show you in a second. And then we do all this transformation in the tree and make this thing more efficient. And in particular, we do lots of things like on computational optimization. I showed some. We do this optimize tick and procs, convert to map, some inlining, all three I showed. And there's vectorization, which I'll show. This is the kind of an interesting one. And then there is the expression optimization. You can do lookup tables. And again, I'll show this one in more details. Inlining, calculate constant expression, and lots of things like, if you see that 3 plus 2, you can change it into 5, right? And you can add these things. And another interesting, nice thing for us was that basically, once you have all this, right, you can instrument the C code to do boundary checks, so you don't violate array constraints. And when you compile in the debug mode, you see that you run it, and whenever you have this boundary array, it's basically memory leak, you fail, right? But you don't want this in a fast version. Obviously, these are techniques that are well known, right? But it's very useful as a physical layer programmer, when you write this and you don't have this tool, right? This will give you this for free. Just a simple instrumentation of a code, which we actually have. It works now. And many times it helps, like, have a memory overflow. It just stops. You always run with this switch on when you test, and when you don't, then you remove it. So here is a simple example. So this is the little bit of Haskell code, and that's the only Haskell code I'll give you. There's no more, and should be very easy. So here is an optimization we want to do. So I'm doing a subarray read from array x, from 0 to length x, right? So obviously this is the array, I'm reading the whole array. So I want to move this into x, okay? It's the simplest possible optimization. And so it's called subarray inline step, right? And I give you an expression, okay? So what this thinks here is a pattern matching in Haskell, and says only trigger. So this is the pattern, and this is what you do if you match the pattern. So the pattern is the following. Forget about this unexpression. This is something internal. But if E, this is the input expression, is of this type, so it matches, this E matches the E array read evals E start length I. So if you think of this before, right? This was this, right? If it matches this form, right? If it matches this form, then you go on. But moreover, you map the values of what was in there to these variables, right? And you keep on matching. So now I map this evals to x, I map E start to 0, and I map this to something which is called length of n. So it's not an integer, it's length of n. So now, if I do that, all that, then I map the particular starting point to 0, and the end to the ending point to m, and this m happens to be the same as n, then I just rewrite this as evals, and evals is just our x. So I wrote here what's what, and there's like the kind of matching in plain English. But basically, it's kind of, the whole transformation is only this much code. More difficult transformation will be more. But the basic thing designer has to do is sit down and think, okay, what can I transform, right? This is a simple one. And of course, we didn't do this randomly. We just found places where it hurts performance a lot. So we just went and said, okay, and this is because you're doing some bit array search or something. When because bit arrays, we operate on bits. I'll show you later. We have to work on bits, right? And this is very expensive. So it's easy to add new transformations. So you can go and think of what you want to add, or you see a big performance penalty, and you add the transformation there. Right. So, okay. I guess any questions about this, or this is probably a bit. Okay. So now I want to talk about two specific optimizations which are kind of important for our particular domain. That this kind of optimization was more general. Like you can do this in any program if you care about it. So now when you think of this execution model, most of the times and I think I had a question from you like previously, like, oh, why don't you put arrays and how do you do these things? So the way we write our code is we say take an integer and then emit integer, or even worse, take a bit and emit a bit. Right? This is hugely inefficient. You want to take a byte, which is in CPU, in Intel CPUs, it's a byte, so you have to take a bit out. It's incredibly expensive. And so in this case, we want to convert this into that. Okay. So, and then inside do some processing maybe. So can we do that? Okay. So the first thing is, can we do that? And so this is doable if we want to do it. So the second question is, why do we want to do it? But this is in principle doable because we have the whole execution model, which is not hard-coding the code, right? If you look at the Sora code, for example, you either write this or that. You cannot change, right? And you have to think when you write your code, okay, what is the width of this I'm going to write there? So if you want to change, you have to go back and change the recalculate. But you first need to sit down and think, what should be the width of my bus here? Is it what is the optimal for the execution? Should I pass 64? And I'll tell you why this is not a trivial problem in the following slide. But you need to design these numbers, and you have to hard code them. So you can't really do that. So you need to do it yourself, and it's difficult to change. Whereas we argue that the compiler should do it. You shouldn't worry. You should just write this, and at the end it should be that, if possible. So why do we want to do that? So the most important thing is lookup tables. So the lookup tables are basically converting bits to bytes. So if we have operational bits like scrambler, and I'll show you that in a moment. If I have a lookup tables in converting bits to bytes, I don't want to do this on a bit, right? I want to convert this in at least 8 bits, and then operate on emits. So here I think there is a bug, I think typo, but you wouldn't notice there should be takes and emits because it's plural, multiple, right? But and then there's a lower overhead of execution model because now if you think we are ticking, we're doing these ticks and process and all that on this each component, right? But if we take 64 elements and then do FFT, right? We do one tick on 64 elements, then do FFT, then do one process on 64 elements. So we amortize it, right? We don't have to do 64 times. And very often these things are, the overhead goes away. You won't even see it, right? And then there is a faster mem copy simply and a better cache locality. This one I don't know how to quantify, but we can see that you're running the same operation again and again. So you have instruction cache, data cache, everything is still hot. Whereas if you go across the whole thing and come back, then you can have get your cache stale. Okay, so why is this a difficult problem? Can I just not blast it to whatever I want to do, and then there's. So here's the thing. So this is our Wi-Fi with a bit more details. This is actually the transmitter. Now this is not receiver. So let me give you a bit more details what it does. So now here the input is in bits. Okay, so input is in bits, and the first thing that comes is a header. So I need to see the header, and I know where in the header is the data rate, right? So when I see the data rate, and so this is a computer which goes to the bits, and well, it's actually wrong. It should actually process these bits. There is something here missing, right? Because these bits, the header has to be sent as well. So it's just missing part. But once it processes the header, right, it then needs to stop and send the message here, saying what is the length of a packet, what is the data rate, okay? And then the rest of the bits, they go either to this or to that. So there is this special if block, which will decide whether this thing goes here or there. The design is a little, I don't know how to design this in blocks, but basically this block controls where this one goes. But it's also the control block. Basically, it's going to send the control message either to this or that. The length of, what is the length of this packet, okay? And now we'll run either this block or that block. So now if you look at these blocks, what do? So this block is CRC. It calculates CRC. So CRC is kind of state machine. It just XORs things and so on. So basically, if you look at the specs, it pretty much operates on bit. You do some kind of, maybe it's byte, but I think it's bits. If you look at a scrambler, we've seen scrambler, we see it again. Takes a bit, does some XORing and something around that, and does bits. 1/2 encoder. So this is the encoder but basically takes 1 bit, produces 2 bits. So this is to protect your data from transmissions, right? And then you have interleaver. So interleaver takes 48 bits and emits 48 bits. So why is it 48? Because it's in the level of an OFDM symbol. So OFDM symbol takes 48 bits. We'll see that later, but basically it takes 48 bits. It just permutes them around. and then it says, and then it does BPSK. So BPSK does is basically converts this one bit into a complex number, which is in INQs. Okay, so that's 1-to-1. But now this is for 6 Mbps. The other one is, I believe, 54 Mbps, right? So if I look at 54 Mbps, so CRC is the same, scrambler is the same. Now the encoder is 3 to 4, okay, because it's a different encoder. I need to take 3 bits, and I need to to encode 4 bits. The interleaver is now much bigger. So why is the interleaver bigger? Because so it does shuffling over that. But let's look at these. Is this first at the modulator? The modulator takes 6 bits and produces 1 complex number. So as I said, the idea on the interleaver is to shuffle around bits that belong to the same OFDM symbol. OFDM symbol has 48 complex numbers. So if I look at 6 times 48, it's going to be 288, right? So that's how these numbers came up. And this is specified in the standard. If you go to the standard, you'll see this is the way interleaver works. So the point being here is that these numbers are not something I came up with. This is in the standard. If you go carefully to the standard, it's there. So there's no optimization. And this is how it should be. This is how you should write your code. You shouldn't think of anything else. This is in the standard. Okay, you have to respect it. So you put these numbers as they are in the code. And similarly here. Now, what is the issue with that? So suppose I want to lift this. Okay, so now I said, okay, let's make this 8 bits. Make this 8 bits. Now, this one, for some reason, I want to do 4 to 8 bits because I want to do a lookup table. So I'll explain this later, but I don't want it to be really big. And this guy, I want to do 48 to 48 bits, and this guy would be 8 bits to 8 complex numbers. So I want to vectorize all this. So that's something I could do manually. So, I can say, okay, maybe it's just easy as that. Now let's look at the other one. Now the other one, has to be 8, 8, 8, 8, 24, 32, 288, 288, 12, 2. Okay? So again, this is the trivial. Now this guy, it has to be 24, right? Because it takes 3 bits input, right? But this guy has 8-bit output, or at least we decided so. And why do we need to have these guys to have the same input? Because we serve them, we serve them with the same data. There's something serving data from here. So this width has to match to both of them. So their width has to match because they get data from the same kind of input. But the output here should match as well, right? So so the key thing is that these things are actually limited by some internal things inside, right? So let me see, sorry. Okay, there's one more thing here which I forgot to mention, is that basically, if you look at this interleaver, right, it has 288, right? So now, so suppose we send 2 bytes in there, and it goes here. So I have 8 bits and 8 bits, 16 bits, or maybe 3, okay? So I'll fill up this guy, I'll fill up this guy, and I'll fill up this guy and get 32 bits, and then I stop. So what happens? I have a stale data. Some data is left here without really being transmitted. So by the definition of this, I need to have enough data to flush this guy, right? This guy is built to work with 288 bits. So something should tell me that, if I vectorize in 28 inputs, right, I need to have enough inputs to make it work, right? So how do I do that? So this is also in the standard as well. So basically, standard specifies that CRC will be padded by 2 16 bits. So it's not trivial. I mean, the reason is, sorry, the reason is that if you don't send at least 216 bits there, you won't have enough, if you do the calculation through all this, to fill the interleaver.
In the transmitter section, we need to have tiny bits for multi-part connection.
Yeah, I didn't do that here, but it should come before that. But it's not important. This was just for the vectorization bit here, right? And this is important because we have an OFDM symbol. So if we don't fill the OFDM symbol, we won't send it. So we'll never receive these bits. So then this guy will actually tell us, okay, this is how much we should send there. And this also is the user input because it's in the specs, right? And so now, what I want to do, and similarly, I need to have at least 24 bits here, because that's what I need for padding there. So I actually, I move that one there. And so, but at the end of the day, okay, I need to make sure that the input here is kind of matching, the output is kind of matching. So in a sense that, so here we can introduce like the conversion from 2 to 8 and so on. But there's lots of rules we have to do in this. We have to check, and I'm not going to give you too many details. I mean, if you're interested, you can, again, we can discuss and so on. But bottom line is, it's not an easy process, and the problem is that you need to respect all these constraints that will cause you to lose, to not have enough data. In particular, for example, even here, if I take too much data in this guy, I will take too much of the header and won't have enough to give to this guy. I might lose some data in process. So we need to kind of carefully do this, to do this dimensioning for this optimization. Okay, so the second one is the lookup table optimization. I think Kuhn had mentioned it last week, so I don't know if you remember or so, but I'll give you kind of a slow overview of that one. So the key optimization, that's the key optimization that makes Sora transmission works, right? And it's quite important because the transmitter works a lot with the bits, right? And if you don't, and this is not the natural environment for it's not the natural environment for CPUs, 32 to 64-bit CPUs, right? So the key idea here is that we have to identify a block of expression that is doing operations on data and has limited input and output size. So in principle, I can use it on any data, but if I have an integer, the input size is 2 to the power 32 is already too large, right? So this really only focuses on binary inputs, on bit inputs, right? And so we want to find in our abstract syntax tree, you can go to this abstract syntax tree and look at every expression in the tree, and you can write a simple function for this and say, okay, what is the number of inputs? What is the number of outputs that we touch? How can we actually transform this in a lookup table? I'll give you an example there. So, and then when we identify this, then we create a lookup table, and really just instead of doing this whole operation, we just do a big table. We look at the inputs and outputs, put it in the vector of reading in the table, and then read from a table that we pre-created. And this is very similar to FPGA compilation if you think of it. I mean, they do the same thing. It's a different language. You write lots of things. They produce loads of lookup tables. They store it in FPGA, and then that's how it's done. So the technique itself is kind of well done, but in this context, it's fundamental to make things work fast enough, and in particular for bit operations, and we absolutely need to use it. That's the... Okay, so let's see the example of the scrambler that we've seen before, right? So in particular here, so again, this is the scrambler code, which basically starts from this state array, and then it goes through the, so these are the internal states. So then I take one bit, right? And then I do this operation on bit. And this operation is quite clean from here, and that's what we discussed before. And hopefully, this is intuitive. I mean, you can see what it works, and you can map to this figure from the specs, and then you emit one bit. So the question is, how do we make this one work better? So basically, what happens is that first of all, what we can realize is that we can transform this one into a vector that will take 8 bits and emit 8 bits. So that's what is done here. So we make it into this auto map. But then we do this for loop, right? Again, we do the first transformation. It's just saying, oh, I can vectorize this up to 8 bits. So instead of taking 1 bit and doing this, I take 8 bits. And then for each of these bits, I do a for loop, and I do my own code. Okay? And so now, I analyze this code here, and I see, well, okay, this code actually is short enough. I can make it a lookup table. Let's see if I have, yeah. So this code here, it's short enough. I can make a lookup table. So I decide to do this whole thing here, and this is the output of a compiler, basically, which it put this LUT here to decide to be a lookup table. So how does it decide that? So look at this code here. So what's in this code here? So you have a variable that goes from 0 to 8. And then there's a vector, okay, which is of size 8 bits, right? This guy here has 8 bits. And then for each of the 8-bit element, we calculate this formula here. So this formula here involves this temp thing, this scrambler thing, and there is this this guy here. So we can look at all the variables, and this is what the compiler does. So this temp thing is really it's a local thing, which never actually gets used anywhere else, right? So if it doesn't get used anywhere else, we don't care, right? It's just a local thing. And then this scrambler state thing, it is actually a state that persists throughout the loops, right? It doesn't get reinitialized. So this is our input, because whenever we come into this lookup table, this scrambler can change, right? It's not an input from a stream, but it's something that can, every time I do a loop, the state will change. So it is an input. If you look at just this code, this is really an input to this code. And then the vect of x really is so where's this guy? This guy is an input as well, right? This is the input that comes from there. And this input is then this whole array, which is also size 8 bits, right? So we can do a fairly obvious, I suppose, calculation of seeing, if you go through this, how many input variables and how many output variables affect this code. So is this kind of analysis clear? Do you know how I calculate this, or do you want me to go slowly? So basically, I mean, see, what are the variables we use here? We use this scrambler state, right? Because this will do something in the code, right? So this is an input variable, right? We have to change this. But this vect j, this loop, right? It's not an input or output variable. It's only internal, right? It doesn't get seen anywhere outside of this code, right? This thing here, right? And similarly, this temp here, it doesn't really get seen anywhere outside of this code. And why? It doesn't get right. This gets here, this guy gets there. So they don't get seen anywhere outside. So we don't count them, but we count everything else that was seen outside of the code. So we count the scrambler state, this guy here, the vect xi25, and we count these two. So now there's difference between input and output, right? So this guy vect yi26, it's just being written into, right? So it's only the output. We never read from it. So we can declare it an output variable, okay? And then scrambler state is also an output variable, but it's also an input variable. So we put it in both. And this guy here is an input variable. Okay, so once I give you these two inputs, right, you can do this code at home and give me the output. I don't need to know what you did, right? You just do it at home, you give me the output. I give you another input, you give me the output, okay? So I can do it two ways. I can either run this code for whenever I have input output, or I can pre-calculate the inputs, the result of this code for all inputs and outputs, and just look up for this, right? And so that's the key idea, and I think that's so the key question here is, does it make sense to do that, right? If I have a big code, right? I mean, I could hypothetically, I mean, conceptually, I can do that for any computation in the world, but of course, only if the inputs and outputs are small, we can do that. But the key kind of thing here is that really our the fact that we write a compiler, so that we have this abstract syntax tree, allows us to go through this and analyze and understand, figure out what are the input variables, what are the output variables, what are their types. So we do all this automatically, right? And we say, okay, this is the so we can actually do it. And so we're looking at this, right? The input variable are these two. They have 15 bits, right? So we need to have 2 to the 15 inputs in our lookup table, right? For every possible input we can have, we need to have an input in lookup table. So when you give me, or when I give you these two variables, right? You give me this big table, and I just put them together, merge them together, and I create an index which I'm going to read into. And then the output is 2 bytes. So whenever I give you one of these big ones, you give me 2 bytes. So the total size of the lookup table is 2 to the 15 times 2 bytes, 64 kilobytes. But that's really not big, right? And it makes things much faster. But again, the thing is that we have the code, so we can analyze this. And we can just do it We can do it fully automatically. We don't have to think what can be optimized and so on. It doesn't have to be an obvious expression, right? The compiler goes through all possible expressions. If this one cannot be vectorized, then maybe just this one can be vectorized, right? It goes through the syntax tree, and you can see potentials that you can't even see. Not all of them will be efficient, though. So it's not super powerful. Usually, you'll intuitively feel some of these expressions. Yeah, so that's the okay. So I'm thinking whether. Okay, let's try this one and then finish with this for today. So, yeah, go ahead.
This lookup table, when would that be loaded into a reference memory or something? So
At the beginning of the, so we had two implementations. One is static and one is dynamic. So static could actually, with the static one we had a huge C files. It would be a static array. And now we have something that when you start the code, it runs all and creates the tables. Because it's a technical detail, right? But either way, it has to be loaded before you even start executing it.
because this example of 64 bytes, but if we have many large number of lookup tables, so the multiplication of I have large n number of lookup tables, each one is those 64K. So would it go beyond the memory that I would have to process this? What are the total memory requirements you have to meet implementation?
That's a good question. So it's actually okay. So one thing that is interesting with all these architectures that we are targeting, and I don't know if Kun discussed this in the Sora description, but basically, if you think of FPGA kind of architectures, your timing is guaranteed, right? You can do everything, and if you design it for a clock cycle, you respect the clock cycle. With PC kind of architectures, all bets are off. In particular, because it's not a real-time operating system. We are running Windows, which is so we're doing kind of tricks for a QoS in internet, right? We are under 20% of utilization, so we hope it's going to go fine. But if it comes to 90, we are screwed. I mean, there'll be problems. And so, so with respect to these tables, it's a similar thing. There is no hard answer. We cannot check that because there is no constraint. We can say this much table can fit in. The OS will accept 7 terabytes, but it's going to be flushed in, and it's going to be spawned on the disk, and we clearly don't want to go there, right? It's going to run, but it's going to be very slow. So there is no clear answer to it, right? Now the thing is that what we do is a kind of as a heuristic is just saying a single lookup table shouldn't be too large, maybe 256K. The other problem with lookup table is if it's too large, you will start missing L2 cache, and it's about 2 megabytes plus, right? So if you make it more than a megabyte, you can see a big penalty of actually, because you're going to randomly jump, right? So it's actually even better to have smaller table than very big one. So you shouldn't be too aggressive creating the size of each table. Then, in particular for the ones we've seen here, I guess the size, some lookup tables actually repeat, so we do some caching and make sure there are not too many of them. And also we've seen like, I don't know, 10, 20 lookup tables in the code here as well. So it's not that much. If you go wild, yes, it can happen. The other thing is also then, with respect to caches, right? If you have enough vectorization, and here I didn't talk about it, but you can vectorize at multiple levels. You can vectorize to make lookup tables, and you can vectorize around lookup table. So if you vectorize, so let's say we have a huge chunk of data, right? But lookup tables is size 8. So we take 8, give it 8, give it there, 8, give it there, right? What other thing we can do, we can take 8, give it there, and pass it down the pipeline. Then we do all the thing, come back up, take another 8, give it to lookup table, and pass it. So what happens when you do this whole thing is that you have a cache miss potentially every time, right? When I have a huge chunk, I just keep querying lookup table. While it's all in the cache, it's then running faster. So vectorization there is helpful, but again, there is no firm guarantee we can give you. And that's the biggest problem. The only thing we see is that we see that we are sufficiently faster than PC, so works fine. Okay. So I guess, okay, let's leave this example for to warm up for tomorrow then. I think, this was an hour, right? So, and then I'll give you tomorrow, basically, I'll give you some code examples. So the idea is that we have a little bit more, give you some numbers on Wi-Fi and so on. And then I want to go through the Wi-Fi design, and on one hand, show you how we can express it in Ziria language, but also really run through the examples with you and show you why Wi-Fi is designed as it's designed. So we can run small, and you'll see how it's actually easy to write this code, write the code and show what are the effects of multipath, what is the effects of channel equalization, why do we do OFDM, what are the kind of rationale behind choosing Wi-Fi. And it's really not the kind of state-of-the-art Wi-Fi design, but it's something that if you want to play with these things, you should know. And I think it's, I don't know, it's maybe a good point to revisit that if you haven't heard, if you heard it before. So yeah, that's all for today then, and see you tomorrow. Hope to see you in the same number. In particular, Peter Lee will be here afterwards, so good incentive to come.
Let's thank
Thank you.